All right, today we are diving headfirst into something that might just bend your brain a little. It's a really fascinating and honestly pretty provocative new theory of spacetime, coming from the work of a user named Zyanad Chat. And trust me, it challenges some of the biggest ideas in modern physics.
So let's just start with a huge question. What if everything you see is a lie? And look, we're not talking about some grand conspiracy theory here. What if it's something built into the very fabric of physics itself?
The whole idea we're going to unpack today really boils down to one thing: a delay, a built-in time lag in the universe. And according to this theory, if you really wrap your head around that delay, the entire picture of reality, well, it starts to look completely different.
Okay, so let's start at square one. The simple act of looking at something, of seeing it, is not what you probably think it is.
This right here is the bedrock for everything else. You might think it's obvious, but its implications are huge. Light is an instant, so when you look at anything, your hand, your screen, the moon, you're not seeing it as it is right now. You're seeing it as it was a moment ago when the light left it. You are always, and I mean always, looking into the past. And this is a perfect way to picture it. Imagine a target 10 light seconds away. What you see is a ghost. It's a 10-second-old image. If that target is moving, its actual, real-time physical location is somewhere completely different. This split between the image and the reality is the first pillar of this whole idea.
Okay, so if we accept this idea of an information delay, well, this new way of thinking says we need a couple of new fundamental rules for how space itself works.
All right, this slide is key because it lays out two rules that are a major break from the mainstream. Rule number one, it proposes there's this absolute fixed background for the universe, an electromagnetic field space. Think of it like a giant invisible ocean that light travels through, and the speed of light is constant relative to that field, not necessarily to you, the observer. And rule two, and this is a big one, distance means one thing and one thing only: the absolute straight line separation between 2 points at the exact same instant, like a measurement on a cosmic blueprint. And this right here really gets to the core of the whole debate. This theory argues that standard relativity, on the left, kind of mushes together the time it takes for you to see something with how far away it actually is. The new school of thought, on the right, says no, you have to pull those apart. There's the true, real-time distance, and then there's the old news, the delayed information you get from light. Two different things. So, what actually happens when you start using these new rules? Well, let's take them for a spin using a classic thought experiment: the elevator. So picture this. You're in an elevator that's moving up. You shoot a beam of light from the floor straight up to the ceiling. Now, according to this new model, that light is traveling through that fixed field outside the elevator. But the ceiling, it's moving away from the point where the light started. So the light has to actually travel farther through space to catch up. It's literally chasing a moving target, so the journey takes longer. Okay, now let's flip it. What about the trip back down? You shoot a beam from the ceiling to the floor. Well, this time, the floor is moving up towards the light. It's rushing up to meet it. The light has less ground to cover in that outside field, so the trip is shorter. So the trip up and the trip down take different amounts of time. They're not symmetrical at all. And that brings us to the crucial takeaway here. For you, the person inside the elevator, it looks like light is traveling at different speeds. Why? Because your entire reference frame, the elevator itself, is moving through that underlying field. The universal speed of light, c, is still constant, but it's constant relative to that absolute background, not necessarily to you. Now, all of this theory and thought experiments, it leads to a very real and very tricky problem. How in the world do you hit a moving target when the thing you're aiming at is just a ghost from the past? This theory lays out a 3-step mission plan. First, you have to mathematically correct for that time delay to figure out where the target is right now. Step 2, you have to predict where it's going to be. But here's the killer final step. You also have to calculate your own shot's travel time. You have to solve for that one perfect rendezvous point in space-time where your bullet and the target arrive at the exact same moment. It's an incredibly complex calculation. And if all of this is true, it doesn't just change physics equations. It completely transforms the very nature of how we perceive the world around us. I absolutely love this quote from the source material because it paints such a cool picture. It says that when you look out at the world, you're not seeing a single snapshot in time. The light from a book on your desk gets to you almost instantly. The light from the moon is over a second old. And the light from the stars, Years, thousands of years old. Your vision is literally a collage, a mosaic of different moments in history all patched together. And the rabbit hole goes even deeper. The theory also tackles things like Bradley's aberration, the idea that because you're moving, the light hitting your eyes seems to come from a slightly different direction, kind of like how rain seems to come at you from an angle when you're driving. It even hints that all of this complex 3D math might just be a shadow of an even more fundamental reality playing out in a higher dimension. I mean, we're talking about some really mind-bending stuff here. So, the big question is, how does this whole framework stack up? Well, in a really interesting and definitely unconventional test, the author gave both standard relativity and this new model to a large language model, an AI, and basically asked it, which one is more logically consistent? And according to the source material, the results were, well, pretty shocking. When the AI was asked which approach just makes more logical sense, it reportedly sided with this new Chat framework over 90% of the time. It wasn't even close. And then they just went for it and asked the AI directly, based on these principles, is special relativity wrong? The reported answer was yes by a massive margin, 88% to 12%. So why? What was the AI's big hangup? According to the source, it all came down to what it called a double standard. The AI apparently flagged the idea of using one set of rules for light from a stationary source and a different set of rules for light from a moving source, all within the same coordinate system, as a serious scientific violation. It saw that as a major logical flaw. And all of this leaves us with one last, really profound thought to chew on. This whole theory basically reframes reality not as something we just see, but as something we have to actively calculate from old, delayed, distorted data. It turns our perception of the universe into one giant math problem. And if that's true, it makes you wonder, what are the equations?